Hi guys, so today's lesson, what we're going to do is we're going to talk about functions and do a little bit of review from pre-calculus and talk about domain and range and composition. Those are kind of our goals for today. What you're going to do is watch the video. I have provided for you a handout that has all of the written information, the typed information for you. So as you're taking notes, you don't need to actually copy everything down that you see, the text. You will be provided that during or through the OneNote notebook. But if you want to add any of your own notes onto your own paper, feel free to do that. You do not need to print this out. I'm going to put it in your class notebook in OneNote, and then you can take whatever you write on your own handwritten piece of paper, take a picture of it, and insert it into the OneNote notebook so that you have it all together. And then that will be your record of this. So kind of think of this as our first way of keeping a digital notebook instead of keeping a paper notebook like we've done in the past. So this will save out us typing or printing a lot of paper out, killing some trees. So today we're going to talk about functions. So a couple of things to think about with functions, which you already know. We have a function is basically a rule that takes an input, does something to it, and gives us an output. The output depends on what you put in and what the function rule is. Now, when we take a look at this, parts of a function, here's your input right here. It's called your independent variable. Your output is over here, your dependent variable. Usually you give the function a function name so that you know which function you're talking about. We use common F, G, H. You can use Greek letters, so don't get too fussed if we start using things like phi and omega and things like that. You have your super special functions, sine, cosine, log, tangent, secant, cosecant. All of those things are going to be special functions that we give special names to so that we know what we're talking about. Now, with functions, as always, what you learned in pre-calculus last year, the rule of 4 is how we approach everything. And even in calculus, we are going to approach everything by looking at it 4 different ways. First, we're going to look at it with our formula. I can tell you the function name and give you a rule algebraically. You're going to be able to plug in an x value, square it, multiply by 3, subtract 1, and you will get your function. We can look at it graphically. We can take a look at, here's your picture over here. We can pull information from the graph. For example, here we have g of 1 is 2. So here's 1. We go up here to the graph, and it has a y value of 2. That tells you the point 1, 2 is on the graph, and g of 1 is 2. If you input 1 into this function, it returns an output of 2, and so on. So g of 2, 2.5, g of 3 is 2. So we can see that over here by looking at the graph. Now, we could also verbally describe functions. So a lot of times when we're getting into our real world examples, we'll start to do things like this example, w of x, the function named w, where you input x, and x is your age, and your output is going to be your weight at that age. So you can, of course, see that it's not going to necessarily be a linear function, but it may increase at different rates at different times. When you hit a growth spurt, maybe when you're home for COVID and you eat a lot of snacks, maybe our weight is increasing at a higher rate than it would be normally. So we have the verbal description. Then we also have the numeric description. So we can look at graphs by looking at tables of values. These tables are typically incomplete. They're just snapshots of certain points that you're looking at on a function or a graph, but it gives you information, your input, your output, your independent variable, your dependent variable that we're taking a look at. All right, now the big thing that we do need to make sure we're always cognizant of, both in calculus and prior to calculus, is the domain and range. So you do want to make sure that you are familiar with that the domain is the set of all possible input values and that the range is the set of all possible output values. So when we're looking at this function, so we can see here that this function starts, first point on the function starts in A. So it's not a function whose domain is negative infinity to infinity. It has a definite subset of real numbers for which is going to be its possible inputs that are there. If I were to pick a number between 0 and a right here, and you would see that there is no graph above or below that line. And so when you look at that function, if I said, maybe a is like 6, and I asked you for f of 1, you would say undefined or does not exist. D and E is our shortcut for that. So those would be our two kind of acceptable statements to say that there is not a point on the graph that corresponds to an input of 1. There is no output that comes from an input of 1 when you're taking a look at it. And then, of course, as we're looking at this, we can, of course, go through each of the inputs between A and B. We'll call those inputs X. And each X has a corresponding Y value that you can look at over here. The input, now notice like a certain input that gives me this height right here, I can have that height at different places. So a function, each X has exactly one Y, passes the vertical line test, but it doesn't have to be true that each Y has exactly one X. You'll remember that's a special property called one-to-one that we talked about before. So as we kind of go through this, we can take a look at the range of X values that are being used and it's kind of like the range. I say that in terms of like interval notation, the interval of X's that are being used and the interval of Y's that are being used. And then we can kind of set this idea that your domain is going to be A to B and your range is going to be C to D. Now, just to kind of quick review for us, let's talk about our interval notation and set builder notation. Now, you do need to make sure that you are familiar with both notations. I'll tell you, we don't care which one we use, just be correct in notation. If you are describing a set, use a correct set notation. Recall that square brackets include the endpoints. Parentheses do not include the endpoints. You can have a closed interval, an open interval, or a half open, half closed interval when you look at it. Remind yourself that when you have infinity, you always use a parentheses because you can't actually equal infinity. It's not a number, it's a destination. So we do want to make sure that we always use parentheses there. So this would be kind of your notation for that. And of course, I didn't put on here, but you can do negative infinity to an upper bound and so on. Intervals whose range has a closed interval like this would be considered a bounded function. If it's something like this right here, you would call it bounded below by A. Both of these are bounded below by A because they don't go any lower than A. Or bounded above could be something like negative infinity to B and so on. So we can talk about this idea of boundedness as well when we start talking about range. All right, so keeping this in mind, if we take a look at some examples, if I have our nice friend, the parabola, x squared plus 1, our range, you assume that there are arrows here and here, that it continues to go. If it's an endpoint, they'll put a dot. But if they just kind of leave it, it will assume that it continues the pattern. And so our domain and our range can be easily found by taking a look at the domain, negative infinity to infinity, but our range is bracket 1 to infinity because it starts at this minimum and it's all the y values above that. This is a simple transformation of a parabola. You could see something like a semicircle, very familiar, where you have basically, you could rearrange this, square both sides, and move the t over, and this would be like t squared plus z squared equals 4, which is kind of like x squared plus y squared equals r squared. So it's the circle centered at the origin. This is a positive square root, which means it's only the top half. If it had a negative square root, it would be the bottom half of a circle. So just kind of reminding you of notations for circles. And again, looking at our domain and range, fairly simple. Our domain, negative 2 to 2. Our range is 0 to 2, taking a look at this picture. Then, of course, we get into functions that are a little bit more complicated, like our rational functions. And in rational functions, we start to have things like vertical asymptotes and horizontal asymptotes, even though I didn't really dot in a horizontal asymptote here. And so when we take a look at our domain and our range, this idea of saying what's being used, you'll see that there's a hole right here in the domain, and there's kind of a hole right there, a value that's not being used both in the domain and the range. So when we set up our interval notation for those, we would say negative infinity to 1, we would use the parentheses, we don't want to include it, and then union 1 to infinity. So that union is kind of combining the two together. Now you could certainly also use set builder notation for this, because you could do the set of all x element of the reals such that x does not equal 1. And so that would be another way to write that using set builder. But for a lot of what we're going to do, we do prefer interval notation. All right, now another thing that we want to talk about with domain and range is that when we are looking at a function like this parabola shifted down one this time, that there's an algebraic domain that we take a look at. But not only do we have algebraic domains, a lot of times when we start doing a real life problem, like here we have this area of a shaded region. And that area has a definite, what's called an implied domain based on the real world application that you're doing. So even though it's exactly the same function, x squared minus 1, it's not going to have the same domain and range as just the basic x squared minus 1. So like for example right here, when you're looking at this area of the shaded region, you'll see that x is the side of the bigger square that you're looking at. Now, of course, area is going to be the area of the big minus this hole in the middle minus 1. So that's how we're getting the x squared minus 1. But now if you think about what values x can be, as this kind of squishes in and x gets smaller, 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 you think to yourself, what's the smallest that x could be? That x has to be at least 1. And of course, the area then would be 0 if x was 1. And we don't really want area to be 0. So if we want to have area, notice that what we've done is we've done a parentheses, and 1 is going to be the smallest value of x, and we're not going to include it because that would give us an area of 0. And then we would allow x to get larger and larger and larger. There's no bound on the x going up. So we made it an unbounded top half and went to infinity. And then, of course, if you went to your range, of course, when x is 1, then there's no area, and that was the 0. But because we're not allowing that or including it, we have a parentheses here and here. And then as x gets bigger, of course, the shaded area gets bigger. So that's what's called an implied domain. And so you do kind of, especially in some of the word problems we look at later on, you're going to want to be able to come up with that implied area as well based on a real life problem. And then we have our more algebraic, more complicated examples. And you kind of have to remember the basic rules that we had for pre-calculus. One here is that you cannot have 0 in your denominator. So division by 0 would not return a defined numbers. So the domain is assumed to be the set of all numbers for which a function is defined. And so here, clearly 0 has to be thrown out. And then the other thing that's here, in addition to a fraction, we have a square root. Even roots, you must have a positive number or 0 under the radical. Well, I already threw 0 out because of the fraction, so really what's underneath of here can only be a positive number, and that's why we restricted our domain to be 0 to infinity. So you look for restrictions based on different types of functions. And so from last year, I'm not going to talk too much about it in this. I'm more concerned with algebraic domains, but logs have restrictions. Trig functions like secant and cosecant, tangent and cotangent have restrictions. So there are different functions that have different restrictions of the special functions, and you do need to be familiar with those. But we'll review those in a later video. All right, here's another example of a real-world problem. We have a stone that we're throwing. Classic Algebra 2 problem where we have height as a function of time. Now, obviously, taking a look at this, we say, what's going to be our domain? Well, we're throwing the ball from a height here of 0. It goes up, and it comes down, and it hits the ground. And so we may be restricting our problem to simply going to be the 0 to 6, the time that the ball is in the air, because we're looking at the upward path of the stone. And then we have this idea of our range. Well, our range, we have a certain maximum height. And from the symmetry and from the basics of this, we have intercepts at 0 and 6. Right in the middle is going to be our maximum for our quadratics. And so I could plug 3 in for height and calculate h of 3. and find out that the maximum height is going to be 45 here. So my domain and my range, notice I'm using brackets. I'm assuming that at time 0, the ball was at, or stone was at a height of 0. I don't know how we're throwing it upward. Maybe we're shooting it out of a little rocket or something. And then it ends when it hits the ground 6 seconds later. And then our range is going to be the 0 to 45 feet, or meters, sorry, that we are above ground when we take a look at it. Now, one of the more complicated types of functions that we're going to look at is this idea of when we start combining the algebraic. The algebraic is always kind of the hardest thing to look at. So when we look at this one, we have the same kind of idea. We have a quadratic, and the quadratic is under a radical. So we have the same issue we had with the previous example that was algebraic. I can't have 0 in the denominator, and I can't have a negative under a radical. So there's two things that we're going to look at here. And I'm doing this as a review because this is a very classic problem that we'll see in calculus. Notice the first thing I'm going to do is I'm trying to figure out what makes the denominator 0. So factoring, getting good factoring skills is going to be important. So I went ahead and I factored the quadratic. So I can look at that and I can write some notes to myself and I can say, for this function to be defined, the product of 2x plus 3 and 2x minus 1 has to be a positive number. It can't be 0 because it's in the bottom of a fraction, and it cannot be negative because it's under a radical. So those are kind of the two things that I'm looking at with this function. Now, obviously, zero product property, very easy to solve. We know that two values that make it 0 are going to be the -3/2 and the 1/2. So we're clearly going to take those out of the range. So then the next thing that we want to do is this idea of how do we determine where the product is positive so that we know which values to keep. And this comes into the idea of where we're going to do a sign chart. Now notice that what I've done is I have added the -3/2 here, and I've added the 1/2 here, okay? Because those are my critical values. The other points that are on there are just kind of laying out the number line. They're not really mean anything for us. Now, notice I went ahead and I just drew a little dotted line down here and here. And notice that I put an open circle here and here. We don't want to include those because they're going to be 0, which will cause a division by 0 problem. Now, I take the first factor, 2x plus 3, and I've just listed it right here, so I'm just kind of organizing my thoughts. And if I pick any number up here in this interval, like 1, and I plug it into 2x plus 3, I would get a positive number. If I pick any number in the interval between the two critical points, like 0 or -1, and plug it in, 2x plus 3 is also going to be positive. And then down here, where I have plug in a number from this interval, like -2, that factor would be negative. So I'm making a little sign chart with that factor. I repeat the process with the 2x minus 1 factor. And so again, it would be positive in the interval from 1/2 to infinity. It would be negative now if I pick either of these numbers to plug in, and then negative down here. So we kind of lay out the cases, the possibilities of the two factors. And then what we know is that when I do the product of each of these factors together, that if I have two positives multiplied, it's positive, and if I have two negatives multiplied, it's negative. And so we can see here that we have positives and positives. And then our final kind of writing our solution, what the domain is, we shade the areas that we want to keep, and then we can write our interval notation that matches this shaded area. Now, when we're doing this, we don't necessarily have to show this much work, but I did want to kind of give you a thorough view of what it is you're actually thinking to yourself. A lot of times in my head, I just go, in this interval, I have 3 intervals to test. I just test each one individually and go negative, negative, negative times negative is positive, and I just put a big plus for that section. So a lot of times you can shorten this down, but this is kind of what we're looking at. All right, the graph of a function, again, going back and taking a look at the graphical representation of a function, set of all points for which the function is defined. And if we take a look at the one that we just did, take any graphing utility and graph it, here's the function again, and you'll see that it has points here up until I get to the -1.5, which is right here. And then nothing is in the middle. So if I did like f of 0, I would get undefined, f of 1, or f of -1, and so on. That would be undefined. So anything in this little section has no graph. And then over here, we start again, and we have this. And so the idea is being able to say, for what x values do I have points on the graph for that? All right, the next thing that we're going to do, the second half of this video introduction from 1.1, we're going to remind you about composition. Composition is where you take one function, g, plug it into another function. So it's a sequence of substitutions that you're going to do. You take your input, you plug it into g first, then you take the output of g, plug that into the function f, and get your final output. Order does matter, and this is just showing you the shorthand notation for that. We're going to show you 3 quick examples here just to remind you a little bit of the algebra of the substitutions. So for example here, f of g of x. I have 3 functions defined. I'm going to take g, which is this function right here, quadratic. I'm going to plug it into f. Now let's take a look at what that looks like. So notice that f, the outside function, wherever there was an x, here and here, I put g here and here. Okay? So I substituted g in. And then in the next step, I went ahead and showed that, well, g was actually this x squared plus 1. So I put that there and there. And then I just did some simplification to come up with my final rule for that. Now, it doesn't really work shown. You can go from here and go all the way over to here as your first step. We're just showing you a little bit of extra detail. All right, let's take a look at the next one. Now I've reversed the order. So I'm doing g of f of x. So now on g of f of x, g is x squared plus 1. So I'm taking f and plugging it into g. F is that fraction, so you see that right there. And now there may be other things about simplifying this. You know, maybe you want to FOIL this out or not, but this is really just a rule. And we have a rule. We may want to work with it a little bit. This one had, you know, combined like terms, so I just did it. This one, there's some debate about multiplying out is not necessarily simpler than leaving it in factor form, so I kind of left it at this point. All right, and then our next one down here, when we take a look at this one, we have our composition of 3 functions. So I have h of g, and that's what's going into f. So notice that f, the fraction, wherever there was an x, I now have h of g. Now g is going into h, and remember that h is this x minus 1. So now it's g minus 1 and g minus 1. So that's what gets put there. And then I went ahead and g, which is x squared plus 1, and then maybe see if you can catch up with this, I just simplified. X squared plus 1 minus 1 is just x squared. And then that's why I have x squared plus 1 there. And then same thing, this ends up being x squared, and then the minus 1 added to that. So there's an idea of algebraic composition that you need to be familiar with. Then the new thing that we have, and we did this a little bit last year, is called decomposition. Work backwards and take a function that is a composition like this. It's very clearly a composition. It's not square root of x, it's the square root of stuff. And so the stuff, we want to decompose it. Now, there's a couple different ways to do it. There's not any one way to do it. The easiest way is to have an outside function, square roots, and an inside function, the quadratic, and just split them that way. And the inside function becomes g, the outside function becomes f. And that's how we get our f of g of x. But we could also do this in a separate way, and we could kind of leave the inside function as this part right here, the 4x squared plus 4x, and leave the minus 3 as part of the outside function. So whatever we take out, and think of that as g of x, that's the input where the x would go, and that's why it's x minus 3. And so that would be another way to do that. And it really just depends on kind of what we're doing and what would be better for what we're doing. So there would be different ways of doing it. You're just getting familiar with it right now. And then this last one I'm doing as an example of where you could do it as 3 different functions. So notice that we basically do the same thing we had up here, and I want to decompose it into 3 functions. So I have a quadratic under a square root in a fraction. So in thinking of it that way and working my way from outside in, the fraction would be the first function. The square root would be the second function, and then the quadratic would be the third function. And that's how I'm getting h of f of g of x. So you could decompose it that way. All right, we do want to look at composition in our rule of 4, taking a look at it. So we could look at this numerically as well. So for example, if I was doing f of g of 5, then I would look at 5 and first find the output for g, which is 1. Okay, and then 1 gets put into f, and now I'm looking for f of 1, and f of 1 is 6. And so that gives me my answer for that one. So you could go through each of these. I'm going to leave that for you to look at. I went ahead and I do have a slide that if you want to pause it and calculate these 3 real quick. But the answers for that, if I go f of g of 4, g of 4 is 3, so I'm really doing f of 3, and f of 3 is 5. And then g of f of 5 ends up being 2, and g of f of 1 equals 1. So you can go ahead and verify that for yourself, that you understand how to graphically compute the composition. Then there's numerically. So we're going to end this example of composition with using tables of values. So I'm not going to do all of these, and there's some other, there's composition and there's multiplication. I'm showing you both because I want you to be clear to know which one you're doing. Like here in A, -3 times h of 0 times g of -3. See how that's a little tiny dot? That's not the open circle, so it's not composition. So if I'm doing that problem, there's my -3. H of 0, we find h, we find 0, we look at the value, which is 2. And then g of -3, so we do g, here's -3, so -2, and then we multiply, we get 12. Let's look at the difference between D and E. I'm not going to do all of these, I'm just showing you a couple of examples. Here, do you see how that has a closed circle? That's a times, that's not composition. So this really means take h of 2, so here's h, here's 2, so h of 2 is 0, times f of 2, and f of 2 is 3. So 0 times 3 is 0 for that one. Now that's different than if I was doing composition. Here I'm doing h of f of 2. So I first calculate f of 2. F of 2 is 3. So that's now become h of 3, and h of 3, here's h, here's 3, h of 3 is -1. All right, now another example just to kind of show you, if I do triple composition, that's this right here. So let's look at K. I'm going to start with f of -1, and f of -1 is 2. Then I'm going to do h of 2, which is 0, and then g of 0, which is -2. So you see how you have the successive substitutions that you're looking at. And then another last example, you could start doing things that are a little bit more complicated like this. I'm giving you that k of x, a new function, is 2x plus 10. And I want to know for what value of x, k of x is equal to f of g of h of -1. So it looks complicated, but we're just going to break this down. So let's kind of look at the work for that. The k of x, which is right here, became 2x plus 10. And then over on this side is my f of g of h of -1. So I'm creating an equation that I am going to solve. And this part over here on the right-hand side is simply a number. I just have to figure out what it is. So I calculated h of -1, and that was 1. Then I calculated g of 1, which was 0, and f of 0, which is -4. So all of this came from using the information up here in the table. And then once I got it to here, then it's just a simple linear equation, and I just solve for x at that point. So that just kind of shows you the examples that we have. All right, so hopefully this is a good introduction. Go back and read, I believe it's pages 1 through 5 in section 1.1 if you want some extra examples of domain, range, and composition. And that will wrap us up for today's lecture.